deeper into what was discussed during part 1 as we talk more in depth. So the last lesson we ended with verifying that the amplitude is the vertical stretch. Whether it be sine or cosine, it's pulling our graph above and below that midline. That midline is the vertical shift of the function. That's the k. It also splits the graph in half. So half above the midline and half below the midline is where that amplitude is coming. We also discussed the b inside the function itself, where we talked about the period. Is it going to be stretched, or is the period compressed so that the oscillation is more quick, or is it more spread out about the period? So in our first example, it says if a sinusoidal function starts on the midline at 0.03 and it has an amplitude of 2 and a period of 4, let's write the formula for the function itself. So you can see I already have written it for us, but how do I get there? So there's a few things that we know. We know that the midline is at the point 0.03. So we know this is what our k value is going to be. We know that our amplitude is 2, so we already know that a is 2, but it has a period of 4. But notice that even though our period is 4, we need what is the b value for inside our function itself. So if the period is 4, using the formula provided, 4 is equal to 2 pi over b. Therefore, b is equal to 2 pi over 4, or pi over 2 when we reduce it down. Now we have all of the pieces that we need for our function. I also notice that it tells us it's sinusoidal, so it's either going to be sine or cosine, but looking at the shape of the graph itself, it follows the pattern of sine. It follows the pattern of sine, just shifted up and squished together. So I'm going to use the sine function. Y is equal to a, which we found was 2. It told us that. Sine of pi over 2, we'll say x. You could put t if you wanted to. It doesn't matter. But if you're checking using Desmos, which I highly recommend we do, we know that it needs the x part. And then our k value of 3. Let's practice another example on slide 2. This time I'm giving you what it looks like, and now we have to identify the function that's graphed here. On the right, you'll see that I do already have the graph listed as -2 sine pi over 4x plus 1, but how do we get there? How do I know that that's what it is? So there's a few pieces that I'm going to look at. I'm going to look at the lowest point. The lowest value is -1 down here, and yet the highest value is 3. So when I kind of cut my graph, finding that midline, the units above the midline and below the midline are 2. So I know then that my amplitude is 2, so we have our a value. We know our midline is the equation y equals 1, so we also know our k value. And thinking about if we were to start here, and how long does it take for us to repeat? We were to come back down and start over again, we would be at 8 units. Or you could start up at the top here. How many units does it take to get back to the top? 8 units, so -2 to 6 is 8 units. So we know our period before we repeat the pattern is 8 units, which means we can find B just like we did on the last slide. B is equal to 2 pi over 8. Which is equal to pi over 4. So we also have our B value. This is the pattern of sine, thinking about where we're starting, except it's just flipped over. It's going down first instead of going up first when I'm looking at sine. So in order to get it to just flip, to vertically flip, we'll put a negative in front of our sine. So our function, we'll use function notation. Oh, cancel. F of x is equal to negative sine our amplitude. This helps us flip vertically so that we're going down first instead of up first. So typically with sine, we would go this direction and come back down. So all it is vertically flipped across the midline. Sine of pi over 4x plus 1. And then it was nice that I used Desmos to graph this so I could verify that the points that they had given me in my homework match the points that I found with the intended equation of the graph. All right. Let's try another one, more of a application problem on slide 3. The London Eye is a huge Ferris wheel in England, which completes one rotation every 30 minutes. So that's going to be important, one rotation every 30 minutes. The diameter of the wheel is 120 meters, but the passenger capsules sit outside the wheel. Suppose the diameter of the capsules, suppose at the diameter at the capsules is 130 meters. We're going to need this 130 meters for the diameter. And the rider's board from a platform 5 meters above the ground. Express a rider's height above ground as a function of time in minutes. All right, so we know all together that thinking about our circle, thinking about our Ferris wheel, that it tells us that what would we call them? The capsules sit outside. So from the capsules to outside, it tells us that it's 130 meters all the way across. So our diameter of the whole entire thing is 130 meters. Therefore, we know our radius would have to be 65 meters, so half of that. But we also have to look at the center of the wheel. Where is that located? The center of the wheel not only is the radius, but it also has to include that we're sitting 5 feet or 5 meters above the ground because it's on a platform. So the 65 represents the radius, where the 5 represents the platform. So this represents 70 meters. And this is representing our midline. When I'm looking at the picture here that they provided to us, I do see that our midline is here, where the center of our circle is sitting. This 65 meters here represents the amplitude. So from the highest point down would be 65 meters. And from the midline down is also 65 meters. So as it's rotating up and down. We also can see that where we start is 5 above the ground because we're on a platform. So from where we start, how long it takes until we start to repeat our pattern again. Our period in this case is 30. But we need to know what is the b value. So using the formula, b is equal to 2 pi over 30 or pi over 15. Thinking about where we're starting, this is the pattern of cosine, except it's going up first instead of down first like cosine typically would. So we're going to reflect cosine just like we did sine in the last example. So the height with respect to time is equal to negative 65 cosine. So this negative reflects vertically. Pi over 15, and I'm using t because it's asking us for time in minutes, so just using the variable t, plus 70, our midline. And clearly I don't know where 70 is. I, for some reason, did 75. Here we go. That looks a little better. All right, let's do another example about a different Ferris wheel. On slide 4. And I'm not even going to attempt that name, but at a fair, it has a diameter of about 70 feet and takes 3 minutes to complete a full rotation. Passengers board from a platform 10 feet above the ground. Write an equation for a rider's height above the ground over time. So they're not telling us that the capsules are outside the Ferris wheel like the last example. We will assume the capsules where you're sitting, kind of like if you go to Shields, you don't go above the wheel of the Ferris wheel, you just stay kind of tucked below all the way around. So we'll assume then that since it's not talking about capsules or anything, we'll still assume that the diameter of our circle is still 70 feet with nothing special going on. Therefore, our radius is 35 feet. And this also gives us the amplitude, how far above and how far below the midline we are oscillating. We know that the center is the radius, but we are on a platform, so plus 10 feet for the platform, or 45 feet altogether. So this gives us our shifting, our K value. You do see that I have our graph here as well, so we can verify that where 45 feet might be. So it'd be 20. So oscillating above and below 35 feet for our radius. Our period we have to figure out here is taken because it takes 3 minutes to go a full rotation. So it takes 3 minutes to go one rotation or make one cycle through. So in this instance, since we're talking about time, so our X value is time, it takes 3 minutes to complete one pattern. So our period in this instance is 3. So B is equal to 2 pi over our period of 3. This is also going to be a cosine if we think about how a rider will get on, it goes up and they come back down. They'll go up, they'll come back down. So just like the last example, knowing that we wouldn't have this graph yet, we're kind of thinking about the pattern it is still going to be a cosine pattern, except it's just flipped, where cosine usually starts at the top and it comes back down. So it's just reflected vertically. We'll still use then negative cosine. Oops. h of t we should start with, our height with respect to time. So negative 35 our amplitude, cosine of 2 pi over 3 times t plus our midline of 45 feet. All right, so we've talked about so far examples of vertical shifting. We've talked about vertical stretching for A and horizontal stretching for B. We've talked, but we haven't talked about what if we want to shift our graph on the X and Y, if we want to shift it left and right. So that's the last phase shift we have to look at, shifting left or right on the graph itself. So I'm looking at this first example, and when we're shifting left or right is when we're going to add or subtract inside the parentheses, whereas that k value shifts us outside, so up and down. Outside, just like other functions that we've talked about in college algebra, shifting left or right comes from inside the function. So sketch a graph of 3 sine of pi over 4t minus pi over 4. I'm going to rewrite this because I want to put it in this form where my b is on the outside and then I'm multiplying by something on the inside to really get that left or right shift. So to do that, I'm going to factor the inside, noticing that they both have pi over 4. So our function is equal to 3 times sine pi over 4 times t minus 1. So if I were to redistribute that pi over 4, we'd get back where we started. But now it's in the form that looks like above. We still have our amplitude of 3. This here is still our b value, so we can find our period if we were to sketch this by hand. 2 pi over b, so 2 pi over 4, or multiplying by the reciprocal. So it takes 8 units to get from the beginning to the end. And this part here tells me I'm going to shift right 1 unit. What I've graphed then down below is just the parent function sine in purple. And I've also graphed the piece that they gave us, 3 times sine of pi over 4 of x minus 1. We can see the amplitude certainly changes because it's getting taller by a factor of 3. We see that the period is also shifting a little bit. So from where we start here to where we get over here takes 8 units to do so. But we can see that the similarities and differences between these two. Whereas we would start here, notice that we're shifting to the right 1 unit to start our pattern 1 to the right. So it's just off-centered a little bit. So just to see similarities and differences. So let's see an example of putting this together when they give us a graph. All right, we have our highest point and we have our lowest point. So our lowest point is -5. Our highest point in this instance is 1. So halfway in between would be 3 above and 3 below, since it's 6 total units to go from the lowest to the highest point. So if it's 3 above and 3 below, we know that 3 here, 3 here. So our amplitude is 3. our midline is at -2, so we also know our K value. How long does it take us to complete one rotation? So if we start here, and how many units? So from 1 to 7 is 6. So our period is 6 units, 2 pi over 6, or pi over 3. So we have a lot of things already. However, notice that our highest point, where we started, we're shifted a little bit. We shifted to the right. Typically, we would have the intersection up here. So we're shifting to the right a little bit, thinking about the parent function. So it could be the following. And this is where it might get a little tricky. It could be 4 different sines or cosines. It could be cosine shifted right 1 unit. It could be negative cosine shifted 2 units left. It could be sine shifted half unit left. Or it could be negative sine shifted 2.5 units right. Well, geez, that's so many different choices. Which one is the right one? They all are the right one. The one I saw right away was easily this cosine shifted right 1 unit. I really saw that one just immediately. Oh, well, this highest point should be tipped over to the left 1 unit. So all I did was just move it to the right. So that is the point in which I'm going to utilize. That's the one that I'm going to utilize. So our function is going to be our A value of 3 times cosine. Our B value is pi over 3. Since I'm shifting right 1 unit, I'll have x minus 1 in my parentheses. And then my midline is -2. You certainly could distribute the pi over 3, but you don't have to. And I have one more example like this using the shift. All right, so my lowest point is at 0, and my highest point is at 8. So I need 4 units above and 4 units below for my amplitude. Which makes it pretty easy to find the midline. So we have our A value, we have our K value. How many units does it take us to go from the start to the end? So over here until we, that's not quite right. It should be well over here. So it takes about 10 units to go from where we start to starting the pattern over again. So our B value is pi over 5. Notice that we're in here in cosine. We should on cosine be over to the left. We should intersect on the y-axis over to the left. So, but I see that I'm shifted to the right because we should be over here. We shifted to the right 1, 2, 3.5 units. So if I'm thinking about cosine, it could be shifted right 3.5 units. It could be another version of sine. It could be another version of cosine, maybe flipped over. So please note that just because I'm finding one function, there could be 3 or 4 other ones that are applicable as well, just depending upon how you're seeing things. So our function is 4, our amplitude. I'm using the cosine one, just shifted. Pi over 5. Since I'm shifting right, x minus 3.5 plus 4. And again, definitely utilize, if they're giving you pictures, utilize Desmos to help verify that the picture is matching what you found the equation to be, as a way to help self-check for yourself. All right, and that ends today's lesson on graphing sine and cosine. We'll focus our energies next week on graphing tangent and cotangent and some of the other graphs, cosecant and secant. So today, 6.1 is just solely looking at sine and cosine.